In the previous video, we used a model-based PID to control the motor. In fact, we used the PID controller designed with the Pole Zero Cancellation method. In this series of videos, I will introduce what Pole Zero Cancellation is, discuss the typical limitations of this approach, and intro two common PID designed with Pole Zero Cancellation. This is your control theory teaching assistant. Pole Zero Cancellation means cancelling out the system's pole zeros with the pole zeros from the controller. The advantage is that we can remove unwanted poles and zeros. However, the disadvantage is that it cannot be used in the poles or zeros are in the right half plane, because Pole Zero Cancellation cannot achieve perfect cancellation. For example, the system will change over time. The parameters obtained from system identification are not perfect, and there is numerical error in the processor's calculations. Additionally, the number of zeros in the controller cannot exceed the number of poles. Otherwise, implementation will be impossible. Moreover, if you pay attention, you'll notice that the representation is the open-loop representation, which means that if the system suffers from external disturbances, the open loop cannot make corrections. Therefore, in most cases, we design in the closed loop. There are two methods. The first is to design the controller using methods like root locus. The second method, which we will introduce today, is the equation-solving method. Taking a first-order system as an example, we can use a PI controller to achieve Pole Zero Cancellation. First, multiply the plant by the PI controller to obtain the open-loop system. We can observe that the system has 1 0 and 2 poles. We want to adjust Kp and Ki so that 1 0 and 1 pole cancel each other, and leaving only 1 pole. From this, we can derive that Ki over Kp equals A. Using the formula, we can determine that the closed-loop system is a first-order system. The desired closed-loop system could be a first-order system with omega bandwidth. The omega bandwidth in the denominator refers to the convergence rate. The omega bandwidth in the numerator ensures that the DC gain is 1, meaning that Y will converge to desired Y. From the closed-loop system, we can derive that B times Kp equals omega bandwidth, and solve for Kp equals omega bandwidth over B. From the open-loop system equations, we can solve for Ki equals A over B times omega bandwidth. In summary, if the system is a first-order system, such as motor speed control or temperature control, you can use a PI controller and apply these two formulas to obtain Kp and Ki. This will transform the closed-loop system into a first-order system with desired bandwidth, meaning that when desired Y is the input, the system will converge to desired Y. Additionally, a higher bandwidth results in faster convergence time. In the next video, I will introduce the PID Pole Zero Cancellation used for second-order systems. See you next time.